unfold.
We are launching into a story today that, it really operates on two completely different timelines, doesn't it?
It absolutely does. You have this one timeline that's all about human ingenuity, right? Decades of calculations, telemetry.
The hard science, the engineering.
Exactly. And then you have this other timeline that stretches out for billions of years. It's about philosophy, about cosmic silence.
Existential stuff. And we are talking, of course, about the ultimate expression of both human ambition and humility, the Voyager program.
It really is a unique mission. It has this irreducible duality. It's what we're calling the dual legacy.
Okay, let's break that down.
On one hand, you've got the hard engineering marvel, celestial mechanics, the discovery of whole new worlds, a reconnaissance mission that's been running for, nearly 5 decades now?
That's the objective truth of the mission.
That's the science. But the other story, the cultural and philosophical legacy, that's where this deep dive is really going to take us.
Because these two probes, Voyager 1 and Voyager 2, they were built for discovery, sure, but they were launched as cultural emissaries.
They're carrying a deliberately curated, a collective memory of our species.
All packaged up and just thrown into the galactic void and designed to outlast every single thing we've ever built here on Earth.
And this duality is just perfectly captured by the two main artifacts that define the whole mission. You have the Golden Record.
Right. The 12-inch gold-plated phonograph.
It's the ultimate outward projection. It's humanity's incredibly optimistic, maybe even a little arrogant message in a bottle.
And on the complete flip side of that, you have the pale blue dot, the photograph that forces us to look inward.
And reckon with our own, physical insignificance. It's the moment the cosmos kind of spoke back to us.
What's so fascinating, and something we'll really get into, is that the creation of the message itself became just as profound as the scientific discoveries.
Oh, for sure. And woven into this massive technological effort is this deeply personal love story.
The romance between the astronomer Carl Sagan and Druyan, the creative director for the Golden Record.
A romance that literally began during the record's creation. And that love, it's physically etched into the disk.
So our mission today is pretty complex. We need to unpack the hard science of how these probes even managed to pull off the most ambitious planetary tour in history. A mission that was, believe it or not, technically canceled.
Right. And then we need to dissect the very specific, sometimes contradictory contents of this artifact that carries a human heartbeat and a declaration of love into interstellar space.
Okay, so let's start with that journey, because the fact that Voyager worked at all, it feels less like advanced tech and more like cosmic coincidence meeting, just sheer engineering foresight.
It really was a right place, right time situation. We have to start with the mechanics of destiny, this planetary alignment that made the whole grand tour possible.
And the origins go back way before the 1977 launch.
Oh yeah, over a decade earlier. In 1964, a doctoral student at JPL named Gary Flandreau was just, doing his work studying orbital mechanics.
And he stumbled onto something incredible.
He recognized a stunning astronomical opportunity. He found this arrangement of Jupiter, Saturn, Uranus, and Neptune that was, for lack of a better term, a cosmic express lane.
An alignment that only happens. Right, what is it?
Once every 176 years. Flandreau's discovery meant that a single spacecraft could, in theory, visit all 4 of those massive outer planets sequentially, something that before was just considered completely impossible.
Or at least prohibitively expensive.
Exactly. And the mechanism that makes it all work is the gravity assist.
The slingshot maneuver. It sounds like something out of science fiction.
It's just elegant physics. So as the spacecraft approaches a huge moving planet like Jupiter, it uses the planet's gravity to bend its trajectory.
Okay, that makes sense.
But it does more than just bend it. The spacecraft effectively steals a tiny, minuscule fraction of that planet's orbital momentum.
It steals momentum from Jupiter.
A tiny bit, yeah. And that transfer of energy accelerates the probe immensely, and it redirects it perfectly toward the next target in line.
So you're basically trading up booster rockets. You're letting Jupiter do all the hard work of getting you to Saturn for free.
Precisely. You save all that onboard propellant, you get the acceleration, you get the redirection. And that increased velocity was the critical factor.
How much time did it save?
Well, without this maneuver, a direct flight to Neptune would have taken nearly 30 years.
30 years? Wow.
With the Grand Tour gravity assist sequence, that same journey could be done in about 12. So this alignment was the single most powerful driver behind the mission.
But the politics of exploration, as they so often do, almost killed the whole thing before it even started.
Right. NASA's initial vision, based on Flanders' discovery, was enormous. They called it the Thermoelectric Outer Planets Spacecraft, or TOPS.
An entire fleet of probes.
A fleet of 4 incredibly robust spacecraft. The plan was meticulous. 2 launches in 77 to go to Jupiter, Saturn, and Pluto, and then 2 more in 79 to hit Jupiter, Uranus, and Neptune.
A monumental undertaking.
Ambitious beyond anything they'd done before. But unfortunately, the golden age of NASA funding was over.
The Apollo money was drying up.
Exactly. By the early 70s, the budget was contracting, and you had this huge internal competition from the space shuttle program, which was sucking up all the oxygen.
And our sources say the Grand Tour project was officially put on the shelf in December 1971.
The price tag was nearly $1 billion, which was just staggering at the time. It was unsustainable, so they were forced into a compromise.
The Mariner Jupiter-Saturn project, or MJS?
Right, a much cheaper mission that was officially only scoped to fly by Jupiter and Saturn. That was it.
Which was then renamed Voyager in 1977, right before launch. But here's the magnificent part, this act of, defiance and foresight that saved everything.
The JPL engineers, they knew this 176-year window was about to close.
They weren't going to get another chance in their lifetimes.
Not a chance. They recognized the immense historical rarity of the opportunity. So the engineers, they essentially disregarded the financial compromise.
Boy, they went rogue.
You could say that. They secretly designed the 2 MJS, the Voyager spacecraft, with the durability, the shielding, the power margins needed for the full Grand Tour. They made sure it could survive the deep freeze out at Uranus and Neptune.
So they deliberately over-engineered everything.
They did. They were betting. They were betting that if the probe successfully completed their primary funded mission at Saturn, the success would be so compelling.
That NASA and Congress would have no choice but to approve the mission extension and find the money to keep going?
It was this quiet, audacious gamble on the power of discovery. And that faith in their own engineering is what turned a 2-planet flyby into the 4-planet Grand Tour.
A gamble that paid off bigger than anyone could have imagined. Okay, let's talk logistics. These are 815-kilogram spacecraft launched on those huge Titan the Centaur rockets.
And even the launch order was tactical, right? It was all designed to preserve that Grand Tour option.
So Voyager 2 launched first.
Voyager 2 launched first, August 20th, 1977. It was put on the slower, more curved trajectory, the one that was necessary to line it up perfectly for those later encounters with Uranus and Neptune, just in case.
And then Voyager 1 launched second, a couple of weeks later, on September 5th.
On a faster, more direct path, that ensured it would actually overtake its twin, arrive at Jupiter and Saturn first, and secure that immediate scientific return on investment.
But to do any of this, they needed power. And a lot of it, for a very long time. Solar panels were obviously not an option.
Completely useless that far out, so they required independent energy. Each spacecraft is powered by 3 multi-100-watt radioisotope thermoelectric generators, MHW-RTGs.
Which is basically a nuclear battery. It runs on the heat from decaying plutonium-238.
That's right. At launch, those 3 RTGs gave them about 470 watts of power. That heat is converted into electricity, which is just enough to run the computers, the big high-gain antenna, and all 10 of the core scientific instruments.
And that's why they're still talking to us almost 50 years later. That resilient, predictable power source.
Absolutely. And that power source enabled a scientific odyssey that, like you said, just completely rewrote the planetary textbooks.
Let's start with the first stop, Jupiter. Voyager 1 gets there in March of 1979.
And the discoveries just started pouring in. I mean, the sheer volume and speed was breathtaking. Before Voyager, the outer solar system was just fuzzy dots in a telescope. Suddenly, we saw active, dynamic worlds.
First thing was the rings.
Yep, V1 confirmed this thin, faint ring system around Jupiter, which proved that rings weren't unique to Saturn. That alone challenged a lot of planetary formation theories.
But the really shocking discovery came from Jupiter's big moons, the Galilean moons.
The most electrifying thing, yeah. V1 captured images of the moon Io, and the data showed these massive, active volcanic plumes erupting from the surface.
Io was erupting. And this was the first time we'd seen active volcanism anywhere other than Earth.
Totally unprecedented. What they figured out was that Io is being heated internally by the immense continuous tidal forces from Jupiter and the other moons. It's constantly being squeezed and flexed.
So that flexing generates enough heat to melt the inside,
creating what is essentially a volcanic hellscape. It proved geological activity could be driven by orbital dynamics, not just by radioactive decay like it is on Earth.
And then there's Europa, the cracked ice surface that changed the entire game for astrobiology.
Europa's surface showed almost no impact craters, which means it's constantly being resurfaced. But it was the cracks, these long, linear fractures. It looked like huge plates of ice had been floating around and refreezing.
Which could only mean one thing.
It strongly suggested a subsurface ocean of liquid water kept warm by those same tidal forces. That was the moment the search for extraterrestrial life shifted dramatically outward, beyond Mars.
The probes move on to Saturn in 1980 and 81, and we finally get a close-up look at that incredible ring system.
And we thought we knew Saturn, but the probes revealed a complexity that was it was like chaotic art. The rings weren't solid bands. They were made up of thousands, maybe hundreds of thousands of individual ringlets.
And they were being held in place by tiny moons.
These little shepherd moons, Prometheus and Pandora, their gravity basically herds the ring particles, keeping the edges sharp and creating these intricate wave patterns. It was the first time we'd ever seen celestial choreography on that scale.
But for Voyager 1, the critical moment at Saturn was the flyby of its moon, Titan. This one maneuver decided the spacecraft's ultimate fate.
Right. Voyager 1 was committed to a very close flyby, dipping within 4,000 miles of Titan. And Titan is unique. It's the only moon in the solar system with a dense atmosphere.
Denser than Earth's, even.
Thicker than Earth's. V1 peered through that orange, nitrogen-rich haze and detected methane and other organic compounds.
And that was so important it was worth sacrificing the rest of the Grand Tour for it.
It was, because Titan's chemistry is thought to mimic the conditions on early Earth before life emerged. It's a natural laboratory for studying primordial soup chemistry. But to get that good look,
the trajectory had to change.
Titan's gravity just grabbed V1 and slingshotted it northward, right out of the plane of the ecliptic where all the planets are. For Voyager 1, the planetary mission was officially over. It was now on a one-way trip to interstellar space.
Leaving Voyager 2, the over-engineered workhorse, to fulfill the engineer's secret ambition.
And it delivered spectacularly. It arrived at Uranus on January 24th, 1986. And this was the toughest encounter yet, just because of the distance and how little power was left to send data back.
Uranus is the weird one, right? Tilted on its side.
It is, and V2 just added new layers of weirdness. It found that Uranus's magnetic field is tilted by a staggering 60 degrees from its axis of rotation, and it's way off center. The whole thing has this bizarre corkscrew shape as the planet rotates.
It also discovered a bunch of new moons, including the really strange one, Miranda.
Miranda's surface was a total puzzle. The images showed these massive jumbled features. It looked like parts of it had been shattered by a huge impact and then just haphazardly reassembled by gravity, like a Frankenstein's monster of a moon.
And then the final planetary target, Neptune, August 1989. After 12 years of travel, what was the expectation for the coldest, most distant gas giant?
The expectation was low. A frozen, quiet, inactive blue ball.
But that's not what it found.
Not at all. It found a surprisingly dynamic wind-swept system. It measured the fastest planetary winds ever recorded and saw this massive rotating storm we called the Great Dark Spot, similar to Jupiter's.
And the final act of planetary discovery was Neptune's moon, Triton.
Triton might have been the biggest surprise of the whole mission. V2 spotted active nitrogen geysers erupting from the surface.
Geysers. On something that cold.
It suggested that even this frigid, distant world, which is probably a captured object from the Kuiper Belt, had some kind of internal heat and geological activity. After that flyby, V2 was directed southward. The Grand Tour was complete.
An unparalleled triumph. And then both Voyagers officially began the Voyager interstellar mission.
Right, aiming to characterize the outer limits of the sun's magnetic influence, the heliosphere.
And they reached that ultimate milestone. They left the solar system.
Voyager 1 crossed the heliopause. That's the boundary where the solar wind slams into the interstellar medium on August 25, 2012. It became the first human-made object to enter interstellar space.
And Voyager 2 followed in 2018. As of late 2025, Voyager 1 is over 170 astronomical units away.
Just think about that. Their signals, traveling at the speed of light, now take nearly a full day to reach us. That is the technological masterpiece. But let's shift gears. We built these incredible machines to explore new worlds. What message about our world did we decide to send with them?
That's the essential transition, isn't it? If the probes are the muscles of the mission, the Golden Record is the soul. It moves beyond pure science and becomes this proactive act of philosophical communication.
Indeed. The Golden Record exists because Carl Sagan and his team realized these spacecraft would survive for potentially 1 billion years or more. They'd be coasting through the galaxy long after all evidence of us might have vanished from Earth.
It's a defiant bid for cultural permanence.
Exactly. And they had a precedent, a simpler attempt. The Pioneer 10 and 11 plaques from the early 70s.
Which were basically just simple line drawings.
Right, line drawings of a nude man and woman and a pulsar map to locate the sun. But the nudity caused this huge controversy, a big backlash, which meant NASA was very careful about the Voyager record.
So Sagan puts together this small, intense committee, Frank Drake, and Druyan, Timothy Ferris, and gives them an almost impossible deadline.
Less than a year to curate a representation of the entire planet and the entire human species. An absurd task.
And their choice of medium, this 12-inch phonograph record, seems almost quaint now.
But it was purely strategic, information density. In 1977, a phonograph offered the most storage. It could carry analog sound like music and greetings, but it could also carry 116 images.
How do you put an image on a record?
You encode it as a sound signal. Basically a series of tones that, if you play them back and scan them correctly, translate into the visual lines of a picture.
The record itself had to be tough enough for deep space and deep time.
It's a gold-plated copper disc inside a gold-plated aluminum jacket, which acts as a shield. Gold is chemically inert. It won't corrode or degrade in a vacuum. This is, by orders of magnitude, the longest-lasting object humanity has ever created.
And it's designed to be played. They included a stylus, a cartridge, and diagrams showing a finder how to do it. But the real genius is the cover. It's a scientific Rosetta Stone.
Absolutely. They had to rely on universal constants. They couldn't assume any finder would understand our language or even our numbering system. So the foundation of the whole thing is the hydrogen clock.
Okay, let's break that down, because that sets the time signature for everything else.
The diagram shows the simplest atom in the universe, hydrogen. Specifically, it shows what's called the hyperfine transition, the electron flipping its spin state.
A fundamental process in physics.
And that transition releases radiation at an incredibly precise frequency, 1420 megahertz. That frequency, therefore, defines a universal unit of time, what they call $.
A cosmic tick of the clock.
Exactly. So when the instructions on the cover tell the finder how fast the record rotates, 3.6 seconds per rotation, that speed is expressed in binary, relative to that fundamental hydrogen time unit. If you understand basic physics, you can figure out the speed and start decoding.
Once you have the time, you need our location. That's the pulsar map.
The map is a starburst pattern with 14 lines radiating out from the center, which represents our sun. Each line points to a known pulsar, a rapidly spinning neutron star.
And the binary code along those lines is the key to both where we are and when we are.
Right. The code gives the pulse period for each of those 14 pulsars, again, measured in those hydrogen time units. Now, because pulsars slow down predictably over millions of years,
An advanced civilization can measure the current pulse rates and compare them to what's on the record.
and by doing that, they can calculate how much time has passed since the record was launched. They can pinpoint our location in the galaxy and the exact launch date, the 1977 epoch. It's genius-level cartography.
And just in case that wasn't enough, they added a backup dating method.
A failsafe. They electroplated a tiny sample of ultra-pure uranium-238 onto the cover.
The radioactive clock.
Precisely. Uranium-238 has a known half-life of 4.468 billion years. So by measuring the ratio of the original uranium to its decay products, a finder can independently confirm the artifact's age, even billions of years in the future.
Okay, now let's go inside this arc of humanity. We start with the spoken greetings.
There are 55 spoken greetings on the record, representing most of the major languages on Earth at the time, and the committee gave the speakers total freedom, which led to this fascinating range of cultural expression.
From the very ancient and formal to the incredibly intimate.
You have the formality of Akkadian, a language that was already dead for 3,000 years, which just says, "May all be very well."
And you contrast that with something like the Korean greeting Annyeonghaseyo, which is asking, are you peaceful?
Or the beautiful Amoy greeting from a Chinese dialect, which asks, "Have you eaten yet? Come visit us if you have time."
Which is just a classic idiom of care and hospitality.
Exactly. It's not just a hello, it's an expansion of genuine concern for a stranger. It shows our capacity for social connection.
And the most hopeful, innocent greeting of all has to be the one in English, spoken by Carl Sagan's 6-year-old son, Nick.
Hello from the children of planet Earth. It just anchors the whole thing in the future.
The greetings are followed by this 12-minute sound essay, The Sounds of Earth, which was designed by Druyan.
And she organized it conceptually, moving the listener through a kind of auditory history of our planet.
It starts with geology.
Right, the primordial sounds of a planet forming. Volcanoes, thunder, wind, rain. Then it transitions to the biological, the sounds of life emerging. Crickets, frogs, the complex songs of humpback whales, and eventually the footsteps of humanity.
And the human section gets very intimate.
It does. You hear footsteps, the steady rhythm of a heartbeat, laughter, which was actually Carl Sagan himself. But then they included sounds that were meant to define us as feeling creatures.
Like a kiss.
Yes, the distinct sound of a kiss, followed by a mother interacting gently with her child. For Druyan, this was non-negotiable. She wanted to transmit evidence of human affection and bonding.
To show we weren't just defined by our science or our wars,
but by our capacity for love. The essay then concludes with the sounds of technology, a train, a tractor, a Saturn V rocket launch, and then finally the sound of a pulsar, bringing the whole narrative back to the cosmic scale.
So we've covered the science and the sounds, but now we have to talk about the heart of the Golden Record, the music. Sagan was convinced this was the single best way to communicate human emotion.
The curation was painstaking. They were trying to balance the high art of the Western world with the vast diversity of global traditions.
And in the Western classical section, one composer really stands out.
J.S. Bach. He has 3 tracks on the record. And this wasn't just about personal taste. Sagan championed Bach for his deep mathematical precision, his structural elegance. He thought Bach's music was the closest thing to a universal language of order that we possessed.
And then Beethoven provides the raw emotion.
He does. They included the first movement of the Fifth Symphony, which is all about defiant struggle, and the Cavatina from his String Quartet No. 13.
Why the Cavatina specifically?
It's intensely melancholic. Sagan described it as conveying this deep sense of loneliness and longing. It was a crucial emotional counterpoint. The record had to acknowledge human sorrow, not just our triumphs.
But the committee worked hard to make sure this wasn't just a collection of European high art.
Oh yeah, the effort for diversity was robust. They included Flowing Streams, a 2,500-year-old Chinese Guquan piece that Druyan fought for. There's an Indian raga, Senegalese percussion, a Peruvian wedding song.
And then there's the one track that speaks to despair and resilience in a way nothing else does. Blind Willie Johnson's Dark Was the Night, Cold Was the Ground.
That track is maybe the most emotionally powerful thing on the entire record, and it's wordless. It's just this moaning slide guitar blues piece from 1927.
Why was that one so important?
It was chosen to represent the profound human experience of loneliness, of despair, but also the deep, soulful resilience you need to survive it. It's the perfect, necessary contrast to the intellectual precision of Bach.
Which brings us to the famous rock and roll debate. Chuck Berry's Johnny B. Good.
That was highly contentious. The folklorist on the team, Alan Lomax, argued strongly against it. He dismissed rock music as just adolescent.
And Sagan had that legendary comeback.
He just said, there are a lot of adolescents on the planet. And that settled it. The song was rightly included as this vital, energetic representation of 20th century youth culture.
But the one they couldn't get, the biggest musical exclusion, is just heartbreaking. They desperately wanted the Beatles.
Here Comes the Sun. The title alone was perfect for a mission heading to other stars. The committee was unanimous. The Beatles themselves apparently liked the idea.
But then corporate reality set in.
The rights were controlled by EMI, and they demanded $50,000 per record, $100,000 for the 2 copies.
$100,000. How much was the whole production budget for the record itself?
$18,000, the entire budget. It's this profound irony that commercial conspites, a purely human concept of ownership limited, an artifact meant for eternity.
That's the perfect example of our limits clashing with our aspirations. But let's get to that deeply personal story, the love story between Sagan and Druyan that's literally encoded on the record.
The creation of the record, that intense summer of 1977, was the catalyst. They were working so closely together and their intellectual connection just deeper. It rapidly became something much deeper.
And it all came to a head in a single phone call on June 1st.
Druyan had just found the final piece of music, that Chinese Guian track, and she called Sagan. And that professional call suddenly turned into this profound personal revelation.
They just declared their love for each other.
At the end of that call, yes. A call where they hadn't even shared a physical touch. They decided to get married. It was this massive emotional eureka moment born from intellectual intimacy.
And they immortalized that feeling almost immediately.
Druyan had pushed for including a human EEG and EKG on the record. The hope was that maybe, just maybe, An advanced civilization could decode the electrical patterns of a human brain and heart.
So she volunteered for the recording session.
A few days after that phone call, and as she was hooked up to the machine for an hour, she was consciously thinking about Earth's history, evolution, all the things the record covered. But underneath all that, she was focusing intensely on the wonder of love, of being in love with Carl Sagan.
So the electrical signature of a woman falling in love is permanently etched into a gold record sailing beyond our solar system.
It is the ultimate secret message, meant to last for billions of years. The track ends with the sound of a pulsar, so you have the universal heartbeat merging with the intimate human one.
That is humanity's outward declaration of love. But the mission had one final profound act that required turning the camera back inward, the pale blue dot.
If the golden record is us speaking optimistically to the cosmos, the pale blue dot is the cosmos speaking back to us, giving us a necessary, brutal dose of perspective.
And this was a long battle for Sagan, right? He proposed this way back in 1980.
Right after the Saturn encounter. He knew the image would have zero scientific value. It was purely for philosophy. And NASA resisted him relentlessly.
Why? What was the risk?
The risk was real. Pointing the camera back toward the sun could have damaged the Vidicon tubes, essentially blinding the spacecraft and preventing it from completing its funded mission at Uranus and Neptune. They saw it as wasting resources on a stunt.
But he eventually got his way.
Only after Voyager 2 had successfully finished the entire Grand Tour in 1989. The scientific mission was done. So on Valentine's Day, February 14th, 1990, Voyager 1, already 3.7 billion miles away, turned its camera inward one last time.
And the resulting image of Earth is famous precisely because it's so physically underwhelming.
It is completely undramatic. Earth is a tiny pale blue speck. It occupies only 0.12 of a single pixel. And it's suspended in this beam of scattered sunlight, which is just an optical artifact. We are literally a dust mote floating in a sunbeam.
And just 34 minutes after taking that photo,
the cameras on Voyager 1 were commanded to power down forever to conserve energy. They were never turned on again. That was the last thing it ever saw.
And it's that profound physical insignificance that gives the image its moral power, which Sagan articulated so perfectly.
He argued that it challenges everything we think about ourselves. Look again at that dot, he said. That's here, that's home, that's us. He framed all of human history through this new lens.
Think of the rivers of blood spilled by all those generals and emperors so that, in glory and triumph, they could become the momentary masters of a fraction of a dot.
It reframes all our conflicts, our posturing, our vanity as utterly absurd. For Sagan, the ultimate point was moral. It underscores our collective responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we've ever known.
So where are these time capsules now? They're still sailing on, but they're deep into the twilight of their operational lives.
We are witnessing the final, quiet phase of an epic story. Those RTGs, the nuclear batteries, are decaying at a slow but steady rate. They lose about 4 watts of power every year.
And the engineers at JPL are basically in a constant state of triage.
A painful, high-stakes game. They're turning off instruments, turning off heaters one by one, just to save those few precious remaining watts for the absolute essentials.
The radio transmitter, basically.
That's the priority. It's a slow fade. The cosmic ray subsystem on V1 was turned off in February 2025. That was the instrument that confirmed it had crossed into interstellar space. These are crucial scientific eyes, now blinded so the machines can just whisper for a few more years.
The ultimate goal is to keep at least one instrument running until when?
The early 2030s, but silence is inevitable. Probably around 2036, the power will finally drop below the level needed to operate the transmitter, and the Voyagers will fall silent forever.
But their physical journey will continue. Ballistics doesn't require batteries.
The dead spacecraft will continue to coast, carrying their golden records through the galaxy. Their destinations are already calculated.
Where are they headed?
In about 40,000 years, Voyager 1 will pass within about 1.6 light-years of a red dwarf star called Gliese 445.
And Voyager 2?
In that same time frame, it'll pass within 1.7 light-years of the star Ross 248. In 300,000 years, V1 will pass near another star. The time scales just... they break your brain.
And that brings us back to the official diplomatic context. There was a message from President Jimmy Carter included on the record.
Right, a printed message which provided that formal framework. And it's a statement that accepts our own potential for destruction while still hoping for the future.
What's the tone of it?
It's very honest. He framed the record as a present from a small, distant world. But then came the crucial admission for the Cold War era. We are attempting to survive our time so we may live into yours.
Wow.
It's an acknowledgement of our self-destructive tendencies, but it's paired with this hope to one day join a community of galactic civilizations. It's a humble, official endnote to the whole thing.
So if we synthesize this entire mission, the dual legacy, we realize the Voyager program is a perfect metaphor for humanity. Flawed, striving, brilliant, and vulnerable.
It's a technological triumph that provides the bedrock of all modern planetary science. But its immortality rests in those two great artifacts. The Golden Record is the idealized self-portrait looking outward, saying, we were here, we were love, we were music.
And the pale blue dot is the honest assessment, looking inward, saying, we are small, we are alone, and we have to do better before it's too late.
And tying it all together is that indelible signature of human connection, the electrical pattern of Druyan falling in love with Carl Sagan. In the face of cosmic insignificance, the mission reminds us that connection and compassion are our most potent features. The Voyagers carry the very best version of us into the night.
Which leads to our final provocative thought for you, the listener. These spacecraft are carrying the best of us into the cosmic night. If the Golden Record is found billions of years from now, long after the pulsar map has gone cold and the images are just historical data, what might an alien intelligence learn about humanity? Not from the science, not from the greetings, but from the wordless moan of Blind Willie Johnson's blues track.
Is the true, essential purpose of the record not to communicate technical information with others at all, but rather to define the best version of ourselves, with all our flaws and resilience, for ourselves? It is a golden legacy of hope, humility, and the determination of one species on a small, pale blue dot to leave a forwarding address.